Good afternoon, good evening, and good morning. Greetings from Stanford University and welcome to the 27th AEC Global Teamwork Final Project Presentation Cyber Event. My name is Renate Fruchter, Founding Director of the PBL Lab and your host for the day. The PBL Lab is the home of the AEC Global Teamwork course I've been teaching since 1993 with partners worldwide. Our vision is to transform our students' tool set, skill set, and most importantly, mindset, moving from working in discipline silos to work as a single, cohesive, interdisciplinary team and develop fully integrated solutions. Our aim is to prepare the next generation leaders and change agents for the future workplace and challenges that they will encounter. What is unique about this class is that it brings together students, faculty, and industry mentors from 5 disciplines: architecture, structural and mechanical engineering, construction management, and life cycle financial management. Students learn to collaborate in globally distributed teams to virtually design university buildings, addressing local hazards such as earthquakes, hurricanes, flooding, local labor conditions. I have to say, this year has been a great pleasure to mentor and work with highly motivated, creative, and committed students from Stanford and 12 university partners worldwide. Given the unprecedented COVID-19 challenges and shelter in place, we are organizing this annual event in cyberspace rather than having everyone back at Stanford for a final great, engaging celebration. In preparation for this year's May 8th cyber event, we had to be creative as we are all geographically distributed over 8 time zones. For this purpose, each global student project team prepared a video story of their project evolution. These stories were reviewed and assessed by 30 industry mentors prior to the May 8th event. I have to say, we miss everyone back at Stanford for this event to celebrate the end of the AEC journey together. Nevertheless, we are really excited to see today at our May 8th final presentation Zoom live cyber event a great turnout of 89 participants that includes the global students and 57 industry and faculty mentors. Each team will present a TED-style project team pitch to give everyone an overview of their proposals, followed by a Q&A discussions of their concepts. But before we dive into very exciting student presentations, I want to extend a big thank you to our industry and faculty mentors, alumni, and owners and sponsors who so generously dedicated their time, attention, and knowledge to our AEC Global students. In collaboration with industry partners, we defined 3 challenges to further foster the students' creativity, focused on sustainability, specifically this year, resilience, integrating project delivery, focused on the question whether to industrialize or not to industrialize, as well as shared risk and reward, and technology innovation, focused on intelligent interoperability between models and disciplines. Winners will be announced at the end of the cyber event, May 8th. So don't forget to visit the PBL Lab Project Gallery website to find out who this year's winners are. Last but not least, a special thanks for the generous support of our technology industry partners that enable us to continue to develop new ways of working and learning by leveraging the latest emerging technologies like VR, virtual reality, AI, artificial intelligence, parametric modeling and optimization, and embed them in the students' new daily work practices that they experience in this global teamwork class. And with that, let's move on to the student presentations.
All right. Hi, everyone. Welcome to Team Pacific's spring presentation. First of all, we would like to introduce ourselves, starting with our architect, Ada, SEs, me and Dimitris, MEP, Lukash, LCFM, Adrian, and then Mary and Piero as CMs. We would also like to welcome our super owner, Renata, our team owners, Kostas, Ishan, Sebastian, Carolina, and Tobias.
Discuss how our team connected over the last 4 months. Starting at Stanford, sitting together around the table, with enormous help from Renate, we formed our team. Less than a week later, we had started to collaborate and navigated the virtual world via Zoom, Discord, and VR. We previously saw working remotely in a globally distributed team as a challenge, but that has become the new normal for us. Especially with the unfortunate situation with the COVID-19, which also resulted in Mary returning to India and added one more time zone to our collaboration. Still, we managed to meet often during the week, either in Zoom or Iris VR, to troubleshoot, walk through with the owners, and discuss new ideas.
We summarized our interdisciplinary collaboration and discovered that our team's major collaborators are our SEs, who are available to meet and discuss. COVID-19 made our schedules flexible, and at times it just took us 2 minutes to meet on Zoom.
Our building is located on site belonging to San Francisco State University and will accommodate their engineering department. In the larger context, the site is located at the edge of the campus, right next to the Lake Merced, which inspired us to take advantage of the lake view while forming our concept. In a smaller scale, our site is situated at the crossroad of the main street. During our site visit in January, we discovered a missing pedestrian connection between Winston Drive and North State Drive.
From an environmental standpoint, San Francisco's highest rainfall is noticed between December and February, while the driest season is from June to August. The temperature stays relatively constant throughout the year.
The site's water table is located 14 feet below grade, and the soil is suitable for shallow foundations. Additionally, the area is prone to earthquakes.
From construction point of view, we have a restricted site. The Bay Area is characterized by high construction and labor costs. The location of the library adjacent to the site makes it a necessity to be conscious of noise restrictions. Also, the height difference between Winston Drive and the North State Drive makes access to the site only possible from the North State Drive.
The goal of the project is to implement a user-oriented design to connect occupants of the building with the neighborhood community while designing the facility that engages the collaboration between people. The goal is to be flexible and prepared to adjust to the needs of the user.
Nature can be interpreted either as a threat that needs mitigation or as an opportunity. Therefore, it is our goal to neutralize any threats posed by nature while taking advantage of what nature has to offer in a sustainable but also innovative manner.
Data is important for design, construction, and operation. It must be shared among all disciplines in order to assure its integrity, accuracy, and consistency. The team must work collaboratively to ensure that the design is ready to be built, operated, and maintained.
We've divided the functions to enhance learning, working, and collaboration as the means to create the connections between students and professors, and distribute the functions on 3 floors connected by the heart of the building, which is the Atrium with central staircase.
We have a timber superstructure and a concrete substructure to maintain consistency. The SEs and CMs collaborated with the architect early on to have regular grids and to standardize the structural members. The major challenge we faced was the 47 feet span of the beams above the auditorium. The team solution was to use double flitch beams. The cantilevers are supported by a combination of glulam braces and continuous flitch beams. Additionally, rocking walls are used to increase the building's lateral resistance.
Our final design presents an educational building with a user-oriented design that provides innovative facility for the engineering department. The building corresponds to nature with green walls and blends in with the site due to the use of natural resources. The most important aspect of positioning the building was to create a connection between levels of opposite streets. From Winston Drive, we connected the building with the bridge, and from the other side by the open plaza. The focal aspect that creates the form of the building is an integrated wooden facade that is crucial for harvesting water from fog and use it for operating in the building.
The day of the future faculty members starts when they enter the site through the main plaza. It functions as a meeting spot and the main outdoor public space. Right after entering the building, we enter the main meeting and collaboration space, which is the Atrium. It enhances the social connections, but also could be used as informal collaboration space for individuals and teamwork. The focal point of the Atrium is the staircase that is essential as a viewing spot to the Lake Merced nearby. To emphasize the Atrium from the outside and the view from inside, we've designed the facade to be free from any shading system.
To prevent the users from the glare effect and overheating, we improved the windows to low E double glazing with a low visual light transmittancy. The gray tint windows stop part of sunrise from passing through the glazing on the south side.
The structural rocking walls are part of an integrated green wall system that create the atmosphere of the Atrium and collaboration spaces. From outside, it cleans the polluted air and contributes to decreasing the amount of CO2 in the air. From inside, the system is covered by living walls that generate electricity for plug load in collaboration spaces. Apart from generating electricity, the system creates also pure conditions as well as the natural cooling. The route through the building leads to the auditorium that accommodates lectures and is the biggest room in the building. Additionally, it can be used as a rental space, and the clear visibility is achieved by the terraced audience.
To design a building with high efficiency, we also need an efficient MEP system. For the primary system, the reverse air heat pump was chosen because of its ability to efficiently heat and cool the building by only changing the direction of flow inside. It also does not emit any CO2 and has low operating costs because it is powered by our PV panels. For the secondary system, we chose displacement ventilation and central air handling unit with heat recovery. To ensure thermal comfort, we designed fan coils connected by a 4-pin system. Here in the auditorium, the displacement ventilation is located on 2 levels to improve thermal comfort. The supply ducts and fan coils are located under the raised floor, while exhaust ducts are placed near the ceiling along the beams.
Passing by the small classrooms, we reach another space that functions as a lecture space, the large classrooms. As a response to a possible pandemic, our building plays the role of shelter for the neighborhood, for which the classrooms can be used due to retractable seating. The advantages of the building for giving shelter are the availability of a kitchen and bathroom facilities, sensors in the building to measure and adjust the air quality, and the building management system, which allows to separate the airflow from other spaces. With the fog catcher and the combination of PV panels and Tesla batteries, we can always provide water and energy. Our ultraviolet disinfection robot, which disinfects the building also in normal waves of influenza, keeps the users healthy. During possible lockdowns, we are insured against the loss of rent.
The external staircase functions as a lecture area for faculty and a cinema or performance area for neighbors. It is directly connected to the cafe so that during warmer days, it can be opened up to the plaza. It is designed as one of the spaces to create additional income for the building.
The building is designed to provide not only educational spaces like classes, but also additional areas for collaboration. Taking the main staircase in the atrium, we reach the first floor where in the western wing, we've situated space fully designated to students' collaboration. It offers multiple options of workspaces, from integrated in the facade individual workspaces through shared team tables to assigned meeting and conference rooms. The communication area is included as activated stand-up brainstorming spots, which we will now use to explain what interdisciplinary challenge we faced in this project.
Due to the fact that the water scarcity is a rising problem in California, we have introduced systems that supports production of water from one of the most common phenomena in San Francisco, the fog. Our design is enhanced by the fog catchers being integrated with the facade and involved all disciplines to collaborate.
The water is collected on 2 layers of the woven mesh covered by substances that firstly ensure that the small droplets easily slide down to the collecting gutter integrated with the mullion of the facade, and secondly, prevent the mesh from being covered by microorganisms. The irrigation system is attached to the columns of the facade and brings the water through pipes to 2 water collectors located underground on site.
Due to maintenance, the fog catcher modules are clicked into the modules of the wooden facade and are mounted with profiles. The windows behind the fog catchers are openable to enable cleaning.
The majority of fog catchers are located on the west and north facade because the wind can increase their efficiency. One of the biggest advantages of Carl the Fog is that it occurs almost every day, so our device can work for the whole year. The adoption of the fog catcher idea, combined with water and gray water collection, allowed us to reduce water consumption by 80%. This system can be used not only for harvesting fog, but also as a shading system. We performed an analysis which showed that the system allowed us to reduce the insulation on the building by 27%, which greatly helps reduce cooling loads.
During a subgroup meeting between the architect, SEs, and CMs, a connection detail for the facade modules was prepared in a way that is structurally sound, easy to construct, and does not negatively impact aesthetics. The blue elements are initially attached to the structure, while the red elements are initially attached to the facade module.
Installation of the facade will begin when the structure is finished. First, we install the facade modules with the crane, and then we need to install the facade finish with the telehandler. Finally, the fog catching net is attached and clicked into the facade.
Another example of using the natural resources on site is using the sun to generate energy from PV panels. We have 376 high-efficient panels, which can produce about 32% more energy than we are using in the building. The rest of the energy will be given to university community to charge the electric cars and to the neighborhood in case of a blackout. We also have Tesla batteries that can store enough energy for about 2 days, which should be enough time to repair the PV panels if they get damaged.
To deal with the challenge of frequent earthquakes, rocking walls were used. During an earthquake, the wall rotates but doesn't bend, so the damage on the wall is minimized. However, the damage is still there, but it's confined to the replaceable Cravingler fuses, which provide ductility and resilience for the system, making the building serviceable after an earthquake event.
We have used the nacelle framework to review the planned schedule that Alice creates with the logistics module and Fuser. This framework helps us identify bottlenecks and reduce the potential risk that could cause construction delays. We have chosen an aggressive schedule that resulted from Alice, which means that we are using a schedule that uses the practical maximum resources for the project. With this schedule, we have modeled the 4D simulation, including the logistics. In this simulation, we show how the building is built and what equipment is required at what time. It also allows it also shows us if there's any conflict between equipment. The simulation has shown us the feasibility of the installation of the crane and also the maximum length of the truck that can enter the site. The crane is used since the erection of level 0 until the installation of a facade. Trucks come and go delivering materials such as columns, walls, beams, and slabs. With the results of the 4D simulation and alleys, we have identified the logistical bottleneck. In this simulation, trucks are delivering the facade modules and interior work materials. After the installation of the facade module, there is a facade finish that must be done with the telehandler. This operation must be done at the end of the installation of the whole facade, where the crane is dismantled and carried out of the site. This is to avoid the conflict between the telehandler and the crane. When the truck with interior work material comes, the telehandler must move to another position. We decided to adopt a less aggressive schedule. This will result on a project duration of 300 days and a total construction cost of 12.2 million.
For possibilities of prefabrication, the facade module with the fog catcher was a major component, but the risks were high. The structure is made of industrialized glulam beams, columns, and CLT panels, which have been made to standard sizes where possible, leading to optimization of freight. The fire rating risk is mitigated by using fire paint, and the risk of phytocontamination during transportation is mitigated by using a hydraulic boom or pressure wash. In our DVD, we estimated the target to be $11.9 million. Due to the design evolutions illustrated in the graph, we arrived at a final estimate of $12.2 million. Despite us being $300,000 over budget, we still add value to the building by reducing LCFM costs, especially with respect to water and electricity.
Here we can see the STV's evolution. Our team met every target and were able to reduce our water consumption by 80%, which is very good with the water problems in California. We are also not only earned LEED Platinum certification, but also have a carbon and energy negative building.
The pie chart in the left corner shows the distribution of our lifecycle costs. It reveals that the costs due to manage the building, like operation and maintenance, taxes, or risk costs, are much higher than the initial construction costs from TVD.
We've prepared a summary of the challenges addressed in this year's edition. We are answering the resilience challenge with very multidisciplinary solutions that create a building ready for the unexpected. We are connecting, storing, and sharing natural resources available on site with our users and the surrounding community. We have a timber structure that is resilient against earthquakes thanks to the rocking walls. We are also collecting water from fog and rain to help with the water shortages in California. The PV farm on the roof produces enough energy for the building and to give back to the community. And this, in the combination with our green walls, has allowed our building to be carbon negative. And finally, in case of an unexpected pandemic, the building is designed to be a shelter for people who need it.
After considering the risks and rewards, we decided to install the fog catcher separately and to pre-assemble the facade assembly module whose kit-off parts include the structure, facade component, and then the fog catcher is clipped. The pre-assembly of the structure will be carried out, which consists of beams, columns, and connections. And this helped us to achieve our industrialization goals: reduction in on-site fatalities and incidents, waste reduction by transport optimization and standardization, 4 weeks of schedule reduction, and time certainty, along with optimization of LCFM costs.
Due to an IPD agreement, we implemented a risk and reward concept regarding the target construction costs from the TVD. The graph shows that we share a reward of $1.2 million with the owners in the financial best case scenario, respectively a risk of $1.2 million in the worst case scenario. To close the loop between AEC, MEP, and LCFM, we elaborated the concept of a digital twin, which combines the virtual model with the physical building. The video shows the benefits of the digital twin during the operation phase in case of an earthquake, with combining a virtual and physical walkthrough by using a VR headset and a HoloLens.
We are very proud to say that we are a part of this generation of AEC Global Teamwork. What we've learned here will help us cope with all the challenges coming in our professions. Not only did we polish our skills in our disciplines, but also we broadened our horizons. We created a global project, which wouldn't be possible without any of us. And this learning process couldn't have been complete without enormous help from mentors and owners. We would like to thank especially to Renate for truly being a super owner and super mentor. Thank you, our owners, for spending the late Sunday evenings with us and co-creating the ideas for the building. Thank you, mentors, for always having time for us to answer our questions and teach us. And thank you all for spending this fruitful time with us. Best wishes from Pacific.
Pacific.